So some of the words you might come across when studying about waves are the wave speed, which is essentially how fast that wave travels, its frequency, which is the number of oscillations per second, its time period, which is the time it takes to complete one cycle of that wave, the wavelength, which is essentially how long that how long one complete wave cycle is, and its amplitude, which is the maximum displacement from the equilibrium position. So how high up it can the maximum distance it reaches from that steady position. And a slinky is, well, it's a device that's used to study longitudinal and transverse waves. And to model a transverse wave, you could just sort of move it up and down, creating that pattern, which will look something like this. And to model a longitudinal wave on a slinky, you could just sort of move it back and forth, which will look something like this. And these areas where they're much further apart, these are called rarefactions, and where they're closer together, these are called compressions, which correspond to the peaks and troughs that you'd find on a transverse wave. And a typical wave might look something like this. Actually, let me draw that better. Okay, one last attempt. It is pretty hard with this drawing tablet, but as you can see, this is one complete cycle of that wave, which means this is, actually let me use a different color here. So this whole thing is one wavelength, and this is your amplitude. And that's about it. And the wave equation is v equals f lambda, where v is the speed of the wave, f is its frequency, and lambda is the wavelength. So microwaves typically have a wavelength of about 10 to the power 9 meters, and they have a frequency. No, sorry, they have a wavelength of 0.3 meters and a frequency of 10 to the power 9 hertz. So using the equation, this equation that we stated over here, the speed of the wave is the frequency times its wavelength, and the frequency is 10 to the power 9 hertz multiplied by the wavelength, which is 0.3 meters. So that's about it's about 3 times 10 to the power 8 meters per second, which is really close to the actual value of the speed of light. Because of course these values I've just taken them off the net, and actual actual frequencies for microwaves lie within a certain range, and these are just the minimum values that I've taken. So that's 3 times 10 to the power 8 meters per second. Calculate the speed of a wave with a frequency of 150 Hz and a wavelength of 1.5 meters. So our frequency is 150 Hz, and our wavelength is 1.5 meters. So the wave speed, which is the frequency times the wavelength, is going to be 150 times 1.5, which comes out to be 225 meters per second. Two 25 meters per second. Yep. The speed of the wave with frequency 16 kilohertz and wavelength 3.5 meters. So kilo is just 10 to the power of 3. So that's 16,000 hertz. So that's going to be, so our frequency, that's 16,000 hertz. And our wavelength is 3.5 meters. So using our nice little equation, that's 16,000 multiplied by 3.5, which is 56,000 meters per second. Actually, I'll just do the working on this document itself. I don't think I need to go ahead and do it separately. Oh, my bad. Wrong place. $56,000 meters per second. This time we have a frequency. Oh, this time we're going to solve for the frequency. So we know that V is equal to F lambda, which means that the frequency is just going to be the wave speed divided by its wavelength. So our wavelength is 2.5 meters, and we're given a speed of 1 million meters per second. So the frequency is going to be 1 million. You could write it in standard form, but I'm just going to write it with all those zeros. So that's going to be a million divided by 2.5. That is 6 zeros. That's about 400,000 hertz. Alright, finding the frequency, and we're given a wavelength of 5 meters, and it's moving at the speed of sound. The speed of sound in air is typically about 340 meters per second. So our frequency is going to be 340 divided by the wavelength, which is 5 meters. So that's about 68 hertz. This time we're finding the wavelength. We know that V is equal to F lambda, which means that lambda is V upon F. And we've been given the frequency as 27 kilohertz, which remember is just 27,000 hertz, because kilo is 10 to the power of 3, so you just multiply whatever that number is by 1,000. It's traveling at the speed of sound, which is about 340 meters per second. So this is 340 divided by 27,000. So that's about 0.0126 hertz. No, meters, because we're finding wavelength. Last question. Light travels at roughly 3 times 10 to the power 8 meters per second. And by the way, this is the answer that we found over here. Exactly the same. Pretty good. But only 2.3 times 10 to the power 8 meters per second through water. If a ray of light has a frequency of 7 times 10 to the power 7 hertz,